Welcome to podcast number 32. Still carrying out chapter 7. I'm hopeful that I can get this done in just 2 of these, and so we'll be done with chapter 7 by the end of podcast number 33. But this one deals with elimination still, specifically E2 elimination. And in this example, or this series of examples, we're going to deal with choosing which side the double bond will form on when it has options. So let's consider this molecule to start out with. So we start by identifying our alpha and beta carbons. So beta is one that's one away from the leaving group. So here's my leaving group, meaning this is the alpha carbon. So it has 2 betas. On one side, you have a slightly more crowded beta, and on another side, you have a slightly less crowded beta. So for instance, on the beta prime, it's 1, 2, 3 H's. On this beta, there's a methyl, methyl, and a hydrogen. So there's only one to choose from. Everything's a sigma bond, so they're free to rotate. So it's not a matter of alignment that we have to worry about. It's a matter of bulkiness, crowdedness. So if it ends up that we use a base that is rather large, for instance, this one, we'll decide whether it's large or small soon. But if this is considered large, it's going to be hard to squeeze in to the more restricted area with the bulky groups, and it might choose beta prime. But if it's small, then can actually fit in here no problem, and it chooses this beta because that leads to the so-called Zaitsev, or more substituted product. But we must use, if this bromine is coming out, let's say, then I must use the H that is back, and I must use the H that is back. So as long as it's anti, which they both are, then we have a choice. So the products it'll form, if it chooses the beta prime, the double bond will be here. And if it chooses the beta, then the double bond will end up right here. So the double bond can either be multi-substituted, 1, 2, 3, so we'll call it tri-substituted, or just one carbon, all the rest are H's, mono-substituted. We learned that Zaitsev's rules tell us the more stable, the more substituted, or conversely, the more substituted, the more stable, and then less substituted, less stable. So this is our so-called Zaitsev's product, and we're introducing a new term called the Hofmann product. The Hofmann product refers to the double bond that is less hindered after the person who came up with this synthesis, ingenuitive way of coming up with this. So we'll talk to a little detail about how that happens, but you got to come up with a way to prefer to take less crowded from the more crowded. So a couple ways we're going to do that. We can either use a really bulky base that'll be too crowded for this side and force it to go here, or a really crowded leaving group. So what Hofmann actually did was use a real bulky leaving group, but we're going to address this in terms of bulky base as well. So if you were to use a small base, and ends up CH2, CH3 is relatively small, not 3-dimensionally crowded. So with a small base done at roughly room temperature, traditional lab temperature, you get about 2/3 of the more substituted and only 1/3 of the less substituted. But as soon as you go to a slightly larger base, the Na and K don't really make a difference. But when I have, instead of 2 H's and a CH3 on the carbon with the O, and I have 3 CH3s on the carbon with the O, that bulkiness, that 3-dimensional space taken up by all the methyl groups, makes it such a crowded base that it's going to be harder to get in and get this H. So it resorts to taking less of that beta, more of the beta prime. I see that this percentage goes up to 70. So one other factor I want to toss in, we know that elimination must be done at a slightly high temperature. But this is where we run into a little bit of trouble, because if you raise the temperature, you have a tendency to go for the more stable product, the so-called thermodynamic product. And so when we do that, we note that what was 70-30 is now only 59-41. And all we did is raise the temperature from 25 to 50 degrees, which is actually a decent amount of energy. If you're in the Kelvin scale, it's about 9% higher in temperature. So it's a pretty good increase. But the key thing here, we're really trying to emphasize, is the small base is going to take the more stable one because it can fit in there. The bulkier base has to take the less crowded one. So it's a kinetic versus a thermodynamic situation. Now we're going to call it a Hofmann product and a Zaitsev product. So let's look a little more carefully at the actual Hofmann, traditional Hofmann, and then we'll get a better bearing on just how we're going to use it in this particular setting. So it doesn't matter whether the base or the leaving group gets bulkier. As long as one of them is getting bulkier, the amount of Hofmann product you get increases. So, as mentioned, the traditional Hofmann reaction. Hofmann elimination started in the following way. Amines by themselves are a terrible leaving group, but what Hofmann found is if you exhaustively methylate it, so what XS stands for is just too much excess amount. So the lone pair on this N is free to attack the carbon and kick out the I leaving group. And in doing so, put one methyl on, and then it gets deprotonated by another amine, and it can come in and attack another and put another one, and then gets deprotonated and still a third one go on. But once you put three on, you have three alkyl groups and then this chain. And we choose CH3s because there is no other H to eliminate. So as far as this carbon goes right here, it has a beta and a beta, but these carbons are just by themselves, these isolated carbons. So he basically made, similar to a tertiary butyl group, which, if you recall, on a cyclohexane is so bulky it can only go equatorial. We have this group, which is so bulky it can only align an anti, or prefers an anti fashion to the rest of the chain. So the bulkiness of this leaving group is going to drive this reaction. Okay, so again, here's my alpha. I have betas here. I really just say beta and beta prime, beta and beta prime. And so it ends up, you have the following going on. It ends up preferring here. And make note, the silver oxide is a base. Metal oxides are basic. Metal hydroxides are basic. So this would be like adding K2O or KOH or NaOH, something like that. But we use silver specifically because silver forms a highly insoluble salt with iodide. So the silver cleans up the iodide, helps remove the amine leaving group, and in doing so leaves behind the double bond. So looking at how this works. So the left hydrogen here, the terminal one, notice that it has 1, 2, 3 H's. It's a CH3. And no matter how it's lined up, this one is there, this one here, and this one here. So this one right here is beta. So the beta one here is anti to the leaving group. So this is the beta one I'm interested in. On this other structure, the problem is this CH3 or C2CH3, so the CH3 over here can actually bend in. It can interfere with those. So there's a lot of steric hindrance. It cannot easily rotate to have the bulky groups gauche to one another. So it has to rotate around to generate this into the anti-position. So I'm basically, in this case, now looking down this bond right here. That's this bond right here. So looking down that bond, it ends up this group, that's your CH2, CH3 right here. There's two H's here and here. This thing has to rotate, so that won't work. So when it rotates to where this group is here. So now it's stable. Now you have the bulkiest groups anti to one another. And because of that, there is no H to eliminate. So the H's that would be eliminated, here's my leaving group. The two H's are gauche. That was gauche drawing on my part. Whereas here it's anti. So only this can align in anti-fashion. So you end up getting almost 99% in this reaction of this one. And again, it's temperature dependent. So when I say that number out there, it's close to, but not necessarily exactly, because I didn't give a specific temperature, but it highly favors this. So even at elevated temperatures, we still are going to favor this instead of the internal. Okay, so that's called the Hofmann elimination, traditional one, where you took an amine and made it trimethylamine, and actually trimethylammonium, a bulky leaving group, and forced it to go to the less hindered side, it being the elimination process. Okay, so let's ask some questions, see how well that went over. So we choose methyl iodide. Why? Well, it's chosen because, well, it only has one carbon, so it can't undergo elimination. It really is that simple. If you have two or more carbons, you can form a double bond. So if you only have one carbon, can't really form a double bond between two carbons if you only have one. It's not that it's good nucleophile or electrophile in that sense. It's not necessarily an amine. It's just an amine is known as being a good nucleophile, not electrophile. and then it's the amines themselves are, when it's fully protonated, it'll be a terrible nucleophile. So basically, long story short, it's not a good electrophile, and it's not, amine is no longer a good nucleophile because of that methylation. I- can deprotonate a quaternary ammonium cation. There's no H on it to deprotonate. If you remember, it had 3 CH3s and the rest of the chain, so that won't help. And then finally, the amine must not be sterically hindered, otherwise it could not undergo elimination. Not necessarily true. That is our goal, is to make it sterically hindered. It avoids Zaitsev elimination, not just elimination in general. So it makes it line up in a way where it's anti to a terminal carbon. So it allows you to get terminal alkenes. Okay, a little bit easier question, hopefully this time. The previous one, I don't know if it's that clear. Go back and run it again and without the sound on. Just pause it and try the question and see if it makes sense. If it takes a second listening, it may. For this question, to synthesize 2-methyl-1-butene using Hofmann elimination process, what amine could be the reactant? Okay, so we first should draw 2-methyl-1-butene. It's a terminal amine. Oh, sorry about this. Meant to say draw it. So let me go ahead and draw this out. So your terminal amine will be 1, 2, 3. Want to have this here. So there's your terminal amine. So let me make sure I understand this. This is carbons 1, 2, 3, 4 with the methyl on top. So it's on carbon 2 as a methyl, and then the butene is double bonds between carbon 1 and 2. We assign the 1 to the less hindered carbon, the first carbon in the chain. So double bond is between 1 and 2. Okay, so, and it isn't that we assign it to less hindered, we assign it to the lowest number priority-wise when counting through, but it is a less hindered in this case. So we have this double bond here, and if we start with this group here, the best we can do is this, with that being eliminated, and on top of that, it's not enough carbons. We're lacking the right amount of carbon, so that one's definitely out. Okay, this next one has the right amount, but it would end up, we did this, here's my group that's going to become really bulky. When it becomes bulky, what's going to happen is it's going to want to preferentially react to the H's on that less hindered side. So that one's out because it'll lead to, let me get rid of, shoot. I'm going to have to get rid of my drawing over here, unfortunately. And so it leads to this compound where the double bond will form. This leaving group will leave, and that will leave, so you end up with a double bond there, like we've shown. Okay, so that is not giving you the double bond where you need it. Okay, the next one, C. C is out because it too will lead to a double bond. I'm sorry, D is one I'm trying to draw. So this one too will lead to H here being eliminated. So same double bond. It's only this one where the N is sticking off the terminal next to the methyl. So for this one, here's my leaving group. Here is my H. And those two leave, you end up with that, which is 1, 2, 3, 4 long chains. So 1 butene with the 2 methyl. So perfect, best answer, drawn here. So I apologize if I'm kind of all over the map. Just not on my game at the moment. Hopefully I will be soon. So which of the following amine or alkenes, excuse me, is not considered to be the Hofmann product elimination reaction? So the small hint you can go by is it prefers a CH3, and an H on a CH3. It's the least crowded you can possibly get. So if you eliminate a CH3, you end up with a CH2, which means it must be terminal. So terminal at the end, terminal, it's at the end, terminal at the end, internal. So that, in essence, added for us. So the least substituted is in most cases, is terminal, like those three. So this is the one that it is not. So out, out, out for the terminals. The non-terminal one, using, dang, I think I got that. Not terminal, so that is the best choice. It still could be potentially considered non-Zaitsev, but in this case, Hofmann would go here, 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 or here, and it's going to be roughly equally substituted, so it's not really a Hofmann. It'd be try-substituted, try, and try. So you can't really get anything on that one. So it can't be considered a Hofmann product because it isn't less substituted than alternatives. Hofmann elimination, because I'm using a base, Ag2O, and in general, if I'm using a bulky base, like we'll do more examples of, it's base. So because it's a base, if I recall, 1, the first letter in the alphabet is A, 2, second letter in the alphabet is B. So acid is E1, base is E2. So I'm good on that, like in this approach. So I know it's an E2 elimination, not E1. And it's the opposite of Zaitsev. So it has nothing to do with the rearrangement. It has to do with the fact you get the less substituted. So Hofmann versus Zaitsev is a question of regioselectivity. Hofmann chooses the less substituted double bond, forms the less substituted by taking the less substituted H. Zaitsev takes the more substituted or more crowded H. Okay, hopefully these questions are falling into place. So want to consider E2 then, and you're definitely going to have to make a choice, a comparison of which H it'll take. But we're going to shift gears to match the book a little bit more. I'm going to focus more on the base than the leaving group. So taught the traditional Hofmann, where you turn the nitrogen of an amine into trimethylated ammonium and just make a really good leaving group out of that. But we can also do it by using bulky bases, like we did with the first example, looking at what percentage you get of the more substituted and less substituted alkenes. So all that, identify alpha, the one with the leaving group, and then identify all the potential beta carbons. So beta carbons with, or beta hydrogens, which are hydrogens on a beta carbon. If they're non-equivalent, then you have to consider the size of the base in the leaving group. If it's a small base and a small leaving group, then you're going to get a Zaitsev product. If you have a bulky base or a bulky leaving group, it'll lead to a Hofmann product. And if both of them are bulky, it definitely will lead to almost exclusively Hofmann, as long as one of them is bulky. So I'm going to focus more on the base in this case. If the product can form a paraplanar alignment of H in the leaving group, they cannot always do that, like we showed with that one example, also with the bulky trimethylamine. But also when you have cyclic systems, ring systems, there's a chance that it cannot rotate up into H being anti and the leaving group being anti on the other side. It might be substitution issues, might be ring strain issues, but somehow, some way, if it cannot get to that alignment, then you can't get E2 elimination. So bulky base. So I wrote out last time, but T-butoxide is this compound. That is just what we've been doing the whole time. So an O- on a carbon with 3 methyl groups, meaning it's tertiary, hence the small t. So these are all bulky. So it's overall bulky base. So K is the plus, O is a minus, so it's a strong bulky base. T-butyl, this is T-butyl. That bulky group will not allow it to substitute, and it forces it to go to the less hindered side. Let me get rid of everything here and say that we're looking at potentially here, here, and here as betas. So there's my alpha with the meso, the O-methylate, the leaving group. I have beta, and beta prime. So betas are terminal. Beta prime has this bulky group here. So it can't align the right way necessarily for that to eliminate. So the bulky base is going to lead to the less substituted. And just want to add one little stipulation on this, and something that you should hang on to as a thought. If you have no optical activity when you begin with, and your reactant over here has no optical activity, and there's no enzyme which provides optical activity, if everything is optically inert, meaning no rotation of plane polarized light, your products must also collectively be achiral. So you can't rotate light. You can't suddenly get chirality without investing some chirality. Okay, so my bulky base leads to a terminal. It could have been either of these, so I could have also had the double bond here or here, as long as it's terminal. When I use any OH, much smaller, because OH is tiny, it's free to take the more crowded H, the one that might have a little bit of trouble aligning anti because of this bulky group here, but we can still do it. So beta prime is fine. So your predominant product is going to be the more substituted alkene. So small base, you're going to get it in this area right here. So these are the H's it'll choose when you use a bulky base. These are the H's you'll choose when small base. So the so-called Hofmann product and Zaitsev product. Okay, time to play some more. Time for you to give these a shot. Hofmann product, Zaitsev product. So decisions you have to make. How big is this group? So CH2 with a CH3, and keep in mind, it's three-dimensionally big that I'm concerned with. CH3, that's going to get in the way, but H's, not so big. So overall then, this, not as big as it could be. So this is going to go by a less hindering fashion, which means it can go to the more substituted or more crowded hydrogen. I'm going to erase and say you get that, but we run into a second trick. There is no beta hydrogen here. It's all methyl groups. So it can't go there. It can only go here. So this, it didn't matter what base we use. So we're going to call it medium, and medium to on the smaller side of medium. But doesn't matter. Note, now though, I have a chiral center, but this elimination got rid of the chiral center, so I can actually lose optical activity. I can get rid of chirality, but it's very hard to introduce it. So if it starts as optically active, it can still finish as optically inactive. So elimination usually destroys chiral centers. So case in point here, we have two chiral centers, and we'll see what happens with them. NaOH is small, so it could do the terminal, or it could do this more substituted one, the one that's going to give you tri-substituted as opposed to monosubstituted. So bulky base would go to less hindered, but a small base can go to the more hindered. So it has on this beta as opposed to beta prime, it has the ability to put an H in back. If H is in back, it's anti to the BR. Note that it's optically active, can rotate plane polarized light because of these two chiral centers. In the end, the double bind you get is going to be in that space between those two. So that's your spot right there. So as a consequence, you've lost that chiral center and that chiral center. Suddenly it's optically inactive. So it's a way to actually prove a quick thumbnail way. We can probably use spectroscopy like NMR to find out more specifically. But at first glance, if it's still optically active, then it meant it would have gone there. If it loses optical activity, it means lost both chiral centers, the bond must have gone there. Last but not least, it's a small base. The H here is going to be thin or gauche with respect to that BR. So in order to line it up the right way, that H that is right here is going to have to be rotated. So this H is in front. It's got to be rotated to and back to rotate CH3 over here and the ethyl up there. So because these have to change positions, the ethyl group here and the methyl here, they have to be in a different position on the final product. So syn alignment, it has to rotate in order to have them anti. When you do that, these two end up in a different alignment. So here we had the groups across from one another, the bulkiest groups. So this was E was my major product. Here, my bulky groups are on the same side. So Z is my favorite, or my favorite product. So medium base, but no H's choose from it went here. Small base, you can go the more substituted. Small base goes the more substituted. So bulky base will get you the Hofmann. Small base will get you the Zaitsev. Medium base, you can get kind of a mixed bag of the different products. Okay, so time to play Name That Product as fast as you can go. So here is my Cl. This is my leaving group. So this is my alpha carbon. So I have a beta here, here, and here. So I'm going to have to make a choice between these two and this one. It's a medium base, so you'll get a mixed bag of both. But because I have 4 H's to choose from here to get a product and only 3 here, I'm going to favor the double bond going here, which would be the same as the other side. But you will get a reasonable amount of the terminal. So medium is still going to go to the slightly more hindered because it's more substituted. Bulky means I can no longer go to those. So we have the same options here and here, and then this big one up here. So now these are a little more crowded right there. So this base is going to plug off that one. So large base gives me the Hofmann. So the double bond is formed here and here. LDA, just going to have to see this enough times to believe it, but LDA stands for lithium. So plus charge, diisopropyl amide. So I'm going to have a nitrogen with a negative, and I'm going to have these bulky R groups. They don't look terribly bulky, but those are massive. So this is a bulky base. So being that it's a large base, which is going to say right there, which means time for me to get rid of everything I just wrote in. LDA is a large bulky base. So with that in mind, it has to eliminate anti. Here's the leaving group here. From this CH3 is syn, so I do have an anti right here. So because of that, I'm good. I can eliminate that H. So I'm going to end up with this. If, however, I go back to using, instead of a bulky base, slightly smaller base, then I'm in good shape. And so I actually should show that it could go either way. So it could go, goes Hofmann. So what I'm saying, actually, let me start from scratch. It could go here. So it's not that it's limited by which side, but because it's Hofmann, it's going to go to that side because that side is now your less substituted side. So it's Hofmann elimination by preference, steric hindrance, not limitations of where the H is. So I do have an alpha carbon here connected to a beta hydrogen that's anti, and a beta hydrogen anti chooses the side that's less substituted. So my whole point in bringing this up, and I should have been clear with that, is it could go here potentially, but it chooses to go to the other spot. Whereas up here, the same situation, it could, because it does have an anti-H, it could go here. Medium base means you're going to get a mixed bag of both, but it probably is going to do this more often than the less substituted. Now we have an issue. Now it's kind of a moot point because no matter what, my H cannot be anti because they're both cis to one another. H cannot be anti. So it ends up, it just isn't going to make a difference. You're going to end up with the Hofmann product, but you're still going to end up with Hofmann product because you do not have an anti-H to deal with here. You can only do the H on that side. So this one isn't necessarily Hofmann because of Hofmann preference. It's Hofmann result because I don't have the H in the right position. So the ever so popular not anti-beta hydrogen trick. Keep an eye out for this one. We like to mess with you with stuff like this. Okay, this was basically one reaction done over and over and over, you having to decide if it's going to go to the more substituted or less substituted side. So when it's a large bulky base, it goes less substituted, the so-called Hofmann product. And if it can, with a medium or small base, like could use NaOET or NaOCH3, so like methoxide instead of ethoxide, that's even smaller, so it would get even more preference for the Zaitsev. So small base, small leaving group, you're going to get the Zaitsev. Large base or large leaving group, you're going to get the Hofmann. That pretty much sums it. So I will see you at the next podcast. Sorry that this one had a little bit of me drifting off, but I'll be much better next time. Thank you. And I will see you at the next one.